right, let's continue on with this. Let me finish up with the fat cat problem. So I rushed through it at the end there. We went through the list of forces. There's only gravity. So I see that gravity's unbalanced. There's nothing upward on it that counterbalances it. So that's why I put unbalanced for A. Next, the whole point of the force diagram is to express F net so that we can apply the second law of motion correctly. So we don't have any numbers here, but okay, we can write an algebraic expression because that's ultimately what we want to be able to do at the AP level. So the F net in the vertical direction is literally Fg. That's the only force I have on my diagram. So now I can say that the acceleration of the cat is simply Fg divided by the cat's mass. Now I can plug in that information if I were to have that. That's the whole idea. If you can do this and translate it to this and then apply it to that, that's our goal. Okay? So, next one. Now we're back on Earth, and the cat falls through the air at terminal velocity. Okay, so that's an important piece of information. Let's go through our forces. So, is there an applied force on the cat? Is there something external to the cat acting on it other than the ones that we've listed below, our list below? And the answer is no. There's nothing external to it. Is there gravity? Yes. There's always gravity almost. Okay, is there resistive force? Yes, it's falling through the air. And since we're at terminal velocity, we know that the acceleration is 0. That's important. So if the acceleration is 0, then we know that the forces acting on a cat must be balanced. All right, that's the first law of motion. If you fall at a constant speed, you have balanced forces acting on you. So that means there's something has to balance that gravity, and that's a resistive force. And so that's going to be an upward force that I'm going to call F of D, drag. I'll just write out drag here, or air resistance. And I'm going to put a little hash marks or congruent marks to indicate that they must be the same magnitude. So from the diagram, my net force, we know it equals 0, but I'm going to express it algebraically, is Fg minus F of the drag. Okay, the minus sign because they're in opposite directions. So, and I'm going to put equals 0. I'm making clear from my diagram, these are the two forces, and I know they're add up to 0 because I was told terminal velocity. So now I can say, well, A is equal to F net over M, and that's simply 0 over the mass, or 0. So we're just being consistent with that. Let's do one or two more, and then I'm going to have you practice on your own. Okay, so the cat is sitting on the floor doing nothing, like cats like to do. Let's do a force diagram. We're not told anything else about it except that it's not moving. Not moving does not mean no force, but it does mean forces are balanced. So that's a connection you always want to make. So applied force, is there anything external to the cat? No, there's nothing really pushing or pulling on it. Well, you might argue the ground, but I'm going to call that something else. There's still gravity, so there's F of G once again down. No resistive forces. It's not trying to slide across the floor, nor is it moving through the air. No tension. And how about a normal force? And the answer is, oh yeah. So the floor is supporting it. The floor is pushing up on it. So I'm going to put a normal force, and that's due to the floor. I'm going to put the object that's exerting it. Okay, this is still the Earth. I'm not going to write the Earth every time for F of G. And since the cat is not changing its motion, it's not accelerating up or down, we know these two have to be the same. So this is balanced because the cat's not changing its motion. The net force is Fg minus Fn. Again, Fn is normal. Net is the sum of all the forces, so don't confuse those. And we know once again that it's equal to 0. Okay, so A is simply 0. I'm not going to write it out like I did here. By the way, back up here, what's the object exerting the force of drag? That's the air, right? So if we want to be consistent about the object exerting it. There was no normal force here because the cat wasn't on the ground. All right, let's do one more. Okay, the cat is dragged across a frictionless floor. Okay, I'm trying to extend the page here. All right, so frictionless is important. So we're treating an ideal situation. Now we're going to introduce for the first time where you have forces acting in two different directions, vertical and horizontal, and you must distinguish between the two. So we still have, let's see, an applied force. Yeah, you could say something is dragging it. We don't know what it is, but there's applied. We'll assume it's going to exert it to the right. So I'm going to call that F applied. Okay, you could put a leash if it's a leash attached to the cat or someone pushing it. So there's some object that's attached to the cat that is exerting this force. It could be a hand, whatever. Okay, gravity. Yes, there is gravity. And understand, this force and this force cannot possibly cancel because they're not in the same dimension. One is vertical, one is horizontal. Is the resistive forces. You could argue there's drag, but we're going to assume that since it's moving so slow, there's no drag. There's no friction. We were told there's no friction. You could say, is there tension? If there's a leash, yes, but we've already taken care of that with the applied force. So if you want to call that a tension because of a leash, you can, but don't count it twice. That's a common mistake. And that just leaves then the normal force. And the cat's sitting on the ground, so there is a normal force. Okay, so are these, and that's it, are these forces balanced or unbalanced? Well, ultimately, they're unbalanced. Okay, but I'm going to expand on that a little bit more down below. So let's do this. So let's look in both dimensions. Let's look at the horizontal. So I'm going to look at sigma, that's sum, in the x direction. The sum of the forces in the x direction is just this one right here because that's the only vertical force. There's nothing, or excuse me, the only horizontal force. So since that's the only force, then my net force in the x direction is simply the applied force. In the y direction, the vertical, we can see that that's going to be Fg minus the normal force. And again, the minus because they're in opposite directions. And we know that's got to be 0 because the cat's not accelerating up or down. So it's unbalanced here, it's balanced here. So there's two ways of answering that. What is the net force? I've done that down here. And then if I want to find the acceleration of the cat, well, I focus on the unbalanced part, right? This right here is my net force. So A in the x direction is F of A divided by the mass of the cat. In the y direction, there is no acceleration, as we explained. Okay, so what I want you to try to do is the right-hand column. In the right-hand column, to save us a little time, we're going to ignore the vertical forces. So all you're interested in are the horizontal forces. I put little velocity vectors here to indicate the direction of motion. Velocity is not a force, so that should not be part of your force diagram or your F net. Once you're done with those, and then on the other side, it gets a little bit more difficult. Now you're going to focus on the vertical forces. Okay, so we have 3 or 4 situations. Do your best with that, and then try to answer the following questions. We'll discuss those in class. Perhaps if I have time, I'll do a follow-up video to give you answers.